Number 1 says draw the 3D solid created by rotating each two-dimensional shape around the axis of rotation that's pictured. So remember, this just means spinning this shape around that dotted line. And so if we take a look here, if we think about spinning, you know that you get a circle when you spin. So you're spinning this around, spinning this around. So we're getting two circles kind of stacked on top of each other and filled here. So this is going to be a cylinder. This one, if we're spinning this way, right? So our spin would get us here and then kind of connect all the way up to this. And so we'd get a sideways cone. This one's going to be off of our axis of rotation. So it's going to be spinning here and here. Okay, and then spinning kind of that whole way. So you're just going to get almost like a toilet paper roll, but it's kind of a hollow cylinder. But I would say like a toilet paper roll or a paper towel roll is kind of, if you can imagine what that looks like, that's what this one is going to give. And then this one, again, we'd be spinning horizontally. So I like to kind of do kind of the closest points because you know this circle is going to have a radius that's the same distance from the axis. So it kind of gives you some reference points of like where it's going to spin out to. And just kind of helps you maybe get the line to follow. But this one's going to look like kind of a sideways vase. Number 2, identify each 3D solid from the nets pictured. So in this case, we see these two triangular polygons. So these are our bases. And then those are connected by rectangles. So this is just going to fold up into a triangular prism. Where this next one has this kind of middle triangle here, and then all of these sides will fold up to one point. So they don't go up to another base. There's just the one base and they fold up to a point. So this one is a triangular pyramid. Next one has a square in the middle, and then the 4 triangles on either side that will fold up to a point. So this one's going to be a square or rectangular pyramid. Then this next one, we can see these two shapes here that are connected by rectangles around the middle. So the base shapes are rectangles, and there's 2 of them. So this one's going to be a rectangular prism. Number 3, name the horizontal and vertical cross sections of each solid. So horizontal in each of these is going to end up being parallel to the base. So if we're thinking about this horizontal cross section, it's going to look something like this. So we get a rectangle for this one. Horizontal cross section here. If we were to just cut horizontally to the base, we would end up with a not a square because it's 4 by 2. So this one's going to be a rectangle again. Next one in the cone, if we cut horizontally, we're going to end up with a circle. In this triangular pyramid, we're going to end up with a triangle. Again, same as the base shape when we cut horizontally. So then for this one, if we cut horizontally, we would end up with a hexagon. Then if we were to go vertically, so now vertically is going to end up being, and why don't let me see, maybe I can duplicate this. Let me just duplicate this so we can get these shapes again. So I can draw the horizontal down here. So now horizontally is going to end, or sorry, vertically is going to end up in each of these, since they're all sitting on their bases, being the same shape as the face. Okay, so those faces that go together. So if we went vertically, okay, it's going to be like this. You're going to end up with a rectangle in this one. In the pyramid, vertically is going to end up being a triangle. In the cone, again, a triangle straight across that base and then back up those sides is going to get you a triangle. This pyramid, if you come down and cut across and go back up, again, you're going to get a triangle. And then for the hexagon, if we were to cut across here and back down and back up, we would end up with some type of rectangle. Number 4, find the volume of each solid, round to the nearest to the nearest hundredth, 2 decimal places if necessary. So for any three-dimensional shape that goes up to a point, remember the volume formula is area of the base times the height and then divided by 3. So we're going to want to find the area of the base shape first, depending on what that base shape is. So in this first one, our base shape is a triangle, and we see for a triangle, remember it's 1/2 the base length times the height. And so the base length in this one is 14, and the height is 6.2 of that base, not the height of the pyramid, but the height of the actual base is 6.2. So then we'll do 14 times 6.2 and then divided by 2. So we get the area of the base in this one is 43.4. So then we'll want the height of the pyramid, okay? And the height of the pyramid here is 10.4. So when we go ahead to do the volume, again, we'll have area of the base times the height divided by 3. So the volume here will be 43.4 times the height, which is 10.4. And then we'll divide by 3 since it's a pyramid. So 43.4 times 10.4 divided by 3 gives us a volume here of 150.453. So we'll leave it at 0.45, and then yards cubed for volume. Next one, our base area, our base shape is a square, a 3x3 rectangle. So a square. So the area of the base is going to be 3 times 3. So just base times height there. So we get 9 for our base area. Then the height of this pyramid is 4. So when we go ahead to do the volume, we'll do area of the base, which is 9, times the height, which is 4, and then divided by 3 since it's a pyramid. And so when we do this, 9 times 4 divided by 3, we will end up with 12, and then yards cubed for volume. Next one, we have a cone. So our area for our base shape is a circle. So we'll want to do pi times the radius squared. So this one gives us the diameter. So make sure that you use the radius of 4. So when we do 4 squared, that's 16 pi. Okay, so 4 squared is 16 times pi is 16 pi. And I'm just going to leave it with the pi. I'll multiply the pi in at the end. And then the height of our cone is 14. So when we go ahead to do the volume, we are going to do 16 pi, the area of the base, times the height, which is 14, and then divide by 3. So again, I'll multiply the pi in now. So we'll do 16 times pi, and I'm just going to use the pi button on my calculator, and then times 14, divide it by 3, and we get 234.572. So we'll leave it as 0.57, and then that will be inches cubed for volume there. Then we want to continue finding the volume of these solids. So these are oblique solids, so they're just kind of slanted, but the volume formula stays the same as a non-slanted three-dimensional figure. So in this case, there's two bases on each of these. So the volume formula is area of the base times the height. So we're still looking to find area of the base, and we're looking to find the height of the three-dimensional solid. This time we don't divide by 2 since it's not going to a point like the last ones were. So take a look at each one's base shape. So in this case, our base shape is a circle. So again, we're going to be doing pi times the radius squared. And so our radius in this one is 4. So we're doing pi times 4 squared. So 16 pi for that base area. And then our height of our shape is here perpendicular to the base. So that's 6. It's not this slanted segment. So be careful that you use the correct one. So volume is area of the base, 16 pi, times the height, which is 6. So then we can just multiply those. And if you multiply the 16 and the 6, you could write this volume in exact form of 96 pi, not 64. So then 96 times pi, you could actually multiply that out to get the decimal version of this, which is 301.59. And then again, volume is in cubic units, so feet cubed. So if you need to leave it in exact form, you can. This one asked for to the nearest 2 decimal places, so we'll just multiply that pi in. Next one, the base shape is a rectangle. So area of a rectangle is just length times width. So we'll be doing 10 times 12. So the base area is 120 millimeters squared. And then the height of the shape is out here at 8. So we'll just multiply those two together to get our volume. So base 120, base area 120 times the height of the solid. So 120 times 8. And we get 960 millimeters cubed. Then the next one, the base shape is a triangle. So again, area of a triangle is base times height divided by 2. Or like I said before, you can do 1/2 times base times height. So whichever one you want, same thing. So the base here is 6, the height is 10, and you can switch those around and then just divide by 2. So we get 60 divided by 2, which is 30 for the area of the base. Then the height of this shape is here at 7. So then volume will be area of the base times the height. Area of the base is 30 and the height is 7. So then our volume is going to be 210 centimeters cubed. Number 5, select all solids with a volume of 40 cubic units. So remember, our 2 volume formulas are to take the area of the base times the height if it's got 2 bases like A and E. And then if it's got 1 base, then it's to do the area of the base times the height and divide by 3. So in this first one, we can see that the base is a rectangle and it's 4 by 5. So the area of our base is 20, and then our height is 2. So 20 times 2 would be our volume, area of the base times the height. So this volume is 40 units cubed. So if the base is 20 and the height is 2, that's going to give us a volume of 40. So when we look over here at solid E, the base area is 30, which is bigger, and the height is bigger. So this one is not going to be 40. That one's going to be too big. Now this next one, okay, our base is a rectangle. So 4 times 2 is going to give us 8 for the base. And then the volume for this one is going to be base times height divided by 3. So that's going to be 40 divided by 3. So solid B does not have a volume of 40. Next one gives us the base area is 15. Then we're going to take that times 8 and divide by 3. Area of the base times the height divided by 3. I can do the 15 divided by 3, which then would be 5 times 8, which is 40. So solid C has a volume of 40. Next one, our base area is a triangle. So our base area is 4 times 5 divided by 2, since it's a triangle. So the base area here is 10. So then our volume is going to be 10 times 12, the height, divided by 3. And 12 divided by 3 is 4. So 10 times 4 gives us 40 for the volume. Number 6, a can of soda can be modeled by a right cylinder. Diego measures its height to be 4 centimeters and has a volume of 144 pi cubic centimeters. Find the can's radius. So we've got this cylinder here, and we know that the height is 4 and that the volume is 144 pi, and we need to solve backwards. So we know that the volume formula for a cylinder is area of the base times the height. And we know a couple of these measurements. So we know that the volume is 144 pi. So we'll plug that in. And then we also know the height. Okay. And so I'm going to put the base formula, because we also know that the base is a circle. So I'm just going to write the area formula for a base, or for a circle, which is pi r squared. And then we know the height of this can is 4. And now we're just going to solve backwards to get this radius. So we can just divide both sides by 4. So 144 pi divided by 4. Really, you can just do 144 divided by 4, which is 36 times pi, equals, and then we have still pi times the radius squared. So now we can divide by pi to both sides, and we end up with 36 equals the radius squared. So then you can square root both of these, and you get that our radius equals 6 centimeters. For number 7, very similar problem, just some different measurements. So we've got a can of soda again, and this time the height is 10 feet. So a big can of soda if it's in feet, right? And then the volume is 1930 feet cubed. So again, we've got volume equals area of the base times the height. So in this case, our volume is 1930. And then we know that that equals pi times the radius squared for the area of our circle, and then times the height, which is 10. So remember that this base shape here, this is area of the base. So that's pi times the radius squared for a circle. So now we'll just start solving. So we can divide by the height. So then we get 193 equals our base area, right? Equals our pi r squared. So now we'll divide by pi and get a decimal here. So 193 divided by pi gives us 61.43 for r squared. So then we will square root that number and get our radius. So once we square root this, we get 7.84 for our radius. And then this says rounded to the nearest tenth. So 7.8 feet for the radius of this can. Number 8, triangular pyramid B is the image of triangular pyramid A after a dilation and a scale factor of 4. Okay, so we've got a scale factor of 4. You can draw a picture of this. I'm not going to. I'm just going to write A and B. So we've got this A shape, and then it dilates into this B shape, and the scale factor is 4. So this just kind of helps me keep track that A is the original, B is the image. Then it tells us that triangle A has a surface area of 55 inches squared. So this is our area. And I'll maybe just write area next to that too. So then our area here is 55 inches squared. And then our volume of A is 72 inches cubed, that should say. So this should say cubed. And now we want to find the surface area and volume of B. Okay, so of the image triangular pyramid. And so we know that when we dilate lengths by a scale factor of K, the area multiplies by K squared and the volume multiplies by K cubed. Okay, so volume is going to multiply by 4 squared, or sorry, area is going to multiply by 4 squared, and volume is going to multiply by 4 cubed. So we'll just do 55 times 16, and that will give us our new surface area. So that's going to be 880 inches squared. And then our volume is going to be 72 times 64, because that's what 4 cubed is. And so 72 times 64 gives us our new volume of 4,608 inches cubed. Number 9 is similar. It tells us that cube B is the image of cube A. So again, we have 2 different shapes. So we have A, which is the starting one, and then B, which is the image. And this time our scale factor is 1.25. And it says if the surface area of A is 96, so we know the area here is 96 inches squared, and then that the volume of A is 216 inches cubed, find the surface area and volume of B. So again, we'll take the surface area and we'll multiply it by the scale factor squared, since we're in area, and the volume will multiply by the scale factor cubed. So you can just do 96 times 1.25 squared, and you'll get your new surface area of 150 inches squared. And then the volume, 216 times 1.25 cubed, which will give us 421.875 inches cubed. Then number 10 is telling us again that we've got a 3D shape, hexagonal prism B, and that is the image of A. So we've got our original shape A, we've got our image B after a dilation by a scale factor, this time of 1/2. And then this time it says if the surface area of prism B, so now they're giving us prism B's measurements. Okay, so the surface area here is 24 meters squared. And the volume of shape B is 56 meters cubed. What is the surface area and volume of the original shape? Okay, so remember we take the original times K, so we multiply to get to this second shape. So then if we're going backwards, we're going to end up dividing. So now we're going to take and divide the surface area by K squared. Okay, and we're going to divide the volume by K cubed because we're going backwards. So we'll do 24 divided by 1/2 squared. and we will get 96 meters squared, which makes sense, right? Since this K value is less than 1, the original should be larger, because that means when we go this way, it's getting smaller. So this original volume should be bigger, okay? Or original surface area should be bigger and original volume should be bigger. So now 56 divided by 1/2 cubed, and we're going to get 448 meters cubed for that one. And again, you can try this. So then you can take this and multiply it by, now multiply this by 1/2 cubed and see if you get the 56, or take the 96 answer that you got and multiply it by the 1/2 squared to see if it gets you back to 24. But remember, when you go backwards, you have to undo it by dividing. Number 11, the volume of a single serving soup can is 8.6 fluid ounces, and the volume of the family size can, which is a dilation of the single serving, is 21.4 fluid ounces. Determine the scale factor. So a couple of things that we're seeing here, we're looking at volume. So this means we're getting K cubed. And then they're wanting scale factor, which is a K value. So then we've got the original. So remember, when you compare this, you want to do the new measurement divided by the original. And when we do this, we're going to be getting K cubed. So new divided by original. And since we're looking at volume, it's going to be K cubed. So the dilated volume is 21.4. The original volume is 8.6. So when we do 21.4 divided by 8.6, we get some long decimal of like 2.48837. So now you're going to want to cube root this so you can get down to just K. So cube root that in your calculator, and you'll end up with a K value of 1.36 if we round to 2 decimal places. So this is your volume factor, and then you got to cube root it to get your scale factor. So then part B says, now if we want to create a supersized soup can by dilating the single serving by a scale factor of 3.5, what would the new volume be? So your original single-sized volume is 8.6 fluid ounces. And now we want to dilate by a scale factor of 3.5 to get to this supersized can. And we want to figure out what this volume is. So remember, we would take the original volume and then we would multiply by the scale factor cubed since we're in volume. And that would give us our supersized volume. So 8.6 times 3.5, the scale factor to the third power. And that would give us a supersized volume of 368.725 fluid ounces. And then the final problem, so given a rectangle with an area of 24 inches squared is dilated by a scale factor of 3, determine a possible length and width of the original and the dilated rectangle to fit the situation. So now this can change, okay? So your answers can be different, but what has to happen is our original shape has to have an area of 24 inches squared. And then our new one has to be dilated by a scale factor of 3. So you have a couple of ways to tackle this. You could just come up with a length and a width for the original. And remember, area is length times width. So the two numbers you choose here have to multiply to 24. So if I just did 12 and 2, that would be fine. Then I need to dilate by a scale factor of 3, which means I just need to multiply each of these by 3. So then this new one would have a length of 12 times 3, which would be 36. And then the new width would be 2 times 3, or 6. So your original length could be, your original measurements could be 12 by 2, and then those would dilate to 36 by 6. And now it doesn't ask you to find the new area, but you certainly could. So 36 times 6 is giving us a new area of 216 inches squared. And if we did 24 times 3 squared, 24 times 9, that would also give us this. So if we took our original times our scale factor squared, that would give us that area of 216 for this one as well. So another way you could have done it is multiplying these, then finding two lengths that multiply to 216 and dividing to go backwards. Okay, so there's a couple different ways to tackle this. Another option for this, so if I write a new set in orange, so again, they just have to multiply to 24. So I could have done 8 by 3. And then when I triple those, so 8 times 3 is 24. 3 times 3 is 9. That's another set that would have worked. You also could have just done 24 by 1, which would then multiply 24 times 3. So if we multiply by the scale factor, then we'd have 72 by 3. Could have had 6 and 4 here, could have done decimals. Okay, there's a bunch of different ways to do this, but ultimately these two numbers just have to multiply to give you this area. Then you multiply those by your scale factor of 3 to get your new lengths.